Hi, grade 12s. Here is question 5. This might actually be a question that you want to skip for now, go away and do some work on complex numbers and then return to, because this is clearly a topic that a lot of you hadn't really revised yet, and it's also got the more challenging parts of the topic within this question. So it's not just a straightforward complex numbers question. Having said that, it's got one of the parts B and C have got the key things to try and work on in complex numbers, which is this idea of combining two waves. So an important question, but one that you might want to hold off for now on. Anyway, for those of you that are ready or have gone away and done some work and returned, let's go for it. 5A should be straightforward. So it was plotting the position of Z on an Argand diagram. So an Argand diagram is a way of showing our complex numbers on a number, not a number line anymore, but a two-dimensional space. So we have a real and an imaginary axis. The real one is here. Normally we'd think of it as an x-axis, and the imaginary one, the y-axis. Our complex number is 1 minus I. So 1 is the real part, negative I is the imaginary part. So I'm going to imagine going along 1 and then down 1. So this is Z. And that was 1 minus I. Okay, then it says express Z in the form A e to the IB, where A and B are exact values. Now, one thing that we can do is 1 minus I on our calculator, and then we do shift and the multiplication symbol. However, those are not exact values. You can try the fraction button. It might do this for you. I know some of you are having issues with getting exact values on your calculator, but the fraction button is your best chance of it just working out nicely. And so here we can see the modulus is root 2, the argument is negative pi by 4. If that's not working for you and you're not getting your exact values, then you need to think of it kind of more with our 2D trig. So the modulus is the length of this line. And the length of that line, negative 1 or negative I. The length of that line we could get by Pythagoras' theorem is 1 squared plus 1 squared and then square rooted. So modulus, which was, I think they gave it as A. This is part 2. So A is the square root of 1 squared plus 1 squared, which is root 2. And we need the the argument, which is this. Just as when we're doing our trigonometric functions and our unit circle, we're moving the negative direction round. Hopefully we can see that that is 45 degrees or pi by 4. So we've gone negative pi by 4. If you can't see that, use SOHCAHTOA and you can get that value. So we've got 1 minus I is equal to root 2 e to negative pi by 4 I. We've expressed it in exponential form. Okay, obviously part A is not just there for no reason. We will need it at some point. So don't just think, oh, I've done it, forget about it. It will come in handy. Let's move on to part B though. Part B, we've got two complex numbers, W1 and W2. We need to add them together. So let me just write them down here. W1 is, where are they? E to the IX. And W2 is E to the IX minus pi by 2. E to the IX minus pi by 2. And we want to add these together. W1 plus W2 is the first one plus the second one. Okay, and it gives us a form that we need to write it in. So you can see that they've ended up taking e to the ix out, and then they've got this complex number inside a bracket. So let's have a look at this. Right, I can see that there is EIX. It's just all a bit muddled at the moment. So let's work on that second term, because the first one we can't really do much with, can we? But the second one we can. So it is e to the ix multiplied by e to the negative I pi over 2. I'd be tempted to put the I at the end of that, but I've written it there already. So I'm just using my index laws, and I've got this as a multiplication. And it makes it easier to see that common factor, because look, now they've both got e to the ix in them. So I can take that out. We need 1 for the first term, and we need e to the minus I pi over 2 for the second one. Oops. It's a silly place to put my bracket, isn't it? Okay, it's not quite the form they wanted. I've got that common factor, but that is not an exponential form, c plus id. That is in our rectangular form. So let's switch it back. The easiest way to do it is to use the calculator. 1 plus e. Oops, try again. E to the negative pi by 2 I. Okay, there we go. We get this. I'm going to interpret that first value as 1. So I've got 1 minus I. E to the ix, 1 minus I. Okay, hopefully we're spotting that we've got 1 minus I up here. Probably going to be coming in handy soon. But that was B part 1. Then it says, hence find the real part of W1 plus W2 in the form A cos x minus, I think that's going to be an alpha rather than an A. So that's what we've got to do now. We've got to find the real part of it. Okay, so we want the real part of this number, W1 plus W2. That's what we're after. Okay, it means finding the real part of this. I can't find the real part of this yet. I need it as just one kind of complex number in its exponential form. So I'm going to use what we did in part A2, and I'm going to substitute that in. Okay, so it's the real part of EIX times, then we had root 2 e to the negative pi over 4 I. All right. So what do we do now? I can find a common factor because both these have e to the I in them. So I'm going to take that out as a common factor. I think I'm going to move the root 2 to the front, and then we'll have our e to the I, and then as they're multiplied, sorry, we're not after a common factor, we're just saying that we've got the same base and we're multiplying them. So we can use our, let's write this a bit more slowly, we can use this as our way of writing it. So we're using one of our index rules. We're using the one that was x to the m times x to the n is adding them together. Okay, so I've added those together. Let's just do one more thing. Let's take out the I and say it's x minus pi by 4. Okay, so now it's in exponential form. In your formula guide, which I'm going to have to tidy up after this, we have something on complex numbers here. We have this form at the moment. We're talking about the real part, and it's saying we want to write it as a cosine function. So I'm going to have to switch it into this trig function. So the real part is going to be the r, which is the same r value, times cos theta, which is the same theta value. So let's go back here. It's going to be the same modulus, root 2, times cos of the argument x minus pi over 4. Okay, so now we've used that A part 2 in B part 1 to come up with B part 2. So the question's kind of all coming together now. Okay, that is a really key technique to try and learn. It's going to be used in context now in part C. We have this, we're introduced to context. We're talking about the current in an AC circuit. And we're told it can be modelled by an equation, I equals A cos BT minus C, where B is the frequency and C is the phase shift. We're given two AC voltage sources of the same frequency. We're given their maximum value, so that will be their amplitude, and we're given the phase shift, that will be the C value. When the two voltages are connected to the circuit at the same time, the total current can be expressed as IA plus IB. Find the maximum value of IT, the total. So we want to start off by doing IA plus IB. So we've been given the amplitude is 12. And we've been given the phase shift of the first one is 0. I'm not going to bother writing that in. So that's my first current. My second one has the same magnitude, has the same frequency, because it says they have the same frequency. But this time we're going to have to subtract pi over 2. Okay, so I think we could probably combine these, couldn't we? 12 cos BT plus cos BT minus pi over 2. And we can say that this is the real part of a complex number. So it's the real part, and we hopefully the idea of it being the real part is quite kind of in our mind, because of part B2 we were finding the real part and it led to that cosine function. So all we're doing is kind of reversing that process. So it's going to be, the real part, I need RE for real, of E to the IBT for the first part of the bracket, plus E to the I BT minus pi over 2 for the second part of the bracket. Now, let's think about where this comes from. Like, this looks like it could end up being loads of work, but there's only 4 marks and there's 2 parts to part C. So that kind of gives me an idea that I've already done some of this work. And if I look over here, I can see that it's really similar to what I've got here. So it means I can really be thinking about this result down here, because that is where it all led. So we've still got that 12, but I'm going to just basically take this result from B part 2. I'm going to say it is root 12 times, and it was root 2 cos, right, it's not x, instead of x I've got BT, and then minus pi by 4. So I've recognised that I was dealing with something that was very similar to B part 1, and so I've skipped all that work and I've taken the result from B part 2. The reason, like one of the clues, as I said, was the fact that it seems like too much work for 4 marks. So what's the maximum value of the total current? Well, it's going to be this. So max equals 12 root 2. Find the phase shift. Oh, that's this part here, isn't it? So phase shift equals pi by 4. Not a straightforward question, but I would really encourage you to make sure that part B of this question is something that you are confident doing.